In the previous video, we discussed about bending stresses, particularly normal stresses due to bending. But now we're gonna discuss about shear stresses due to bending. Maybe you are wondering how it's possible that exists a shear stress in addition of normal stress, since we talked about bending a lot and never talked about shear stress. Okay, but exist, and we're gonna derive the expression to find the shear stress in a certain point P. And maybe you also wondering what is that strange Q on the formula. Okay, we gonna respond these questions step by step. Let's start. First, we have to remain that in a beam we consider and generate the shear and bending moment diagrams, isn't it, for different x coordinates along the beam. And there is a neutral surface and a neutral axis that remains the original length. And at the same time, the bending moment generates tensile stress in one part and compression stress in the other, one below and the other above the neutral axis. Yeah, and if we study not the 3D view but the 2D view or side view, we can appreciate some details. For example, the point P is located at a distance, the point P of study is located at a distance y from the neutral axis, the dotted line. And if we study just this tiny part, we can appreciate the compression stresses and the tensile stresses at both faces. But we're gonna change again for the 3D view here. Using the stresses, it's possible to find the force acting on a point that we are studying, the P point, and that force is obtained by multiplying the stress by the cross-sectional area. So we can do the same for both faces. But before go dive, let's remain the example of the aircraft. The wings are beams and the lift is there. It's a distributed load, and we can generate the shear force and bending moment diagrams, isn't it? If we study a particular section of that beam, we can note that. Okay, let's detail better. We can note that on this tiny section is not the same, the bending moment at the both faces. You know, this face, the right face and the left face, support different amount of bending moment. Let's see this. This is the bending moment along the x direction, you know, the change in bending moment along the x direction, and the right face support a bending moment m, while the left face support a moment m plus dm. It means are different. Since the bending moment is different, we can note that stresses are different. We derived this expression in the previous video. Normal stress is equal to moment, bending moment, times y over I, moment of inertia. And if we apply on this tiny section, we can note that stress at the right side is equal to this, while stress at the left face is this, because the bending moment is m plus dm, as we note here, isn't it? So we can also remain that in the previous video we used this expression, normal stress is equal to force divided area, and we can use that for find the force as stress times area, isn't it? So this force and this force are different because this force is equal to stress times area, and the stress in this case is smaller than the stress at the left face. So we have a problem, because if we are looking for equilibrium and both forces are different, we can check that sum of forces are equal to minus sigma prime, this is sigma prime stress, times area, is the same area since this is a really tiny element, yeah, plus the other force, sigma times area. That is, so we have not equilibrium at all here. We have not equilibrium. So what happened? What happened with the equilibrium? We know that there is an equilibrium, but maybe we are forgetting something. So let's check if there is something else. Look, when we bend those sheets, we can appreciate that this line turns into an enormous line, showing that sheets are slipping one over the other. It could make us think a body, a part like this, constituted by layers. So we have to think elements like this, parts as this, bodies as this. It means that when we analyze the stress at point P due to bending, we have to consider not only the normal stress my over I, but also a shear stress, because the body is trying to divide into layers, slipping one over the other, isn't it? And this stress is caused in the area that could be estimated or calculated as thickness times the length of the beam. This observation is very important so as to determine the equilibrium of this tiny piece, tiny part of the beam. Let's check again. The sum of forces, the force pointing to the left is greater than the force pointed to the right, isn't it? As we mentioned before. So this force is equal to sigma prime times area, and this force is equal to sigma times area, isn't it? And this sigma prime is equal to m plus dm y over I, and this sigma is equal to m y over I, isn't it? Okay, let's check the equilibrium. We learned that in addition of this, okay, let's substitute the stress, the normal stress, by its expression m times y over I, and since we are considering the whole section, the whole area of the sectional of the cross section, we have to add a new force, that is the shear force. And how could we get that shear force? Since there is a shear stress, and shear stress is equal to shear force divided by area, the shear force is equal to shear stress times A, isn't it? So we could substitute here, and that's the equilibrium. The force that point to the right plus the shear force is equal to the force point to the left, isn't it? Just simplifying this part is equal to this part, and we get this expression. Yeah, this part passes to the other side, isn't it? And we could isolate the shear stress. Just remain that dm, this is the bending moment, by dx is the shear force, and the integral of y times dA we're gonna call q. This is not the moment of inertia, since the moment of inertia requires the y squared, but it's quite similar, so we're gonna call it q, or first moment of inertia. That is y bar a. Let's resume. The shear stress on a beam could be estimated or calculated using this expression: shear force times Q divided I times T, where I is the moment of inertia of the whole area respect to the neutral axis that passes through the centroid of the cross section. T is the thickness. For example, if we are studying the stress at point P, is the thickness right there. Yeah. V is the shear force obtained by the shear force diagram, and Q is this. If we are studying the point P, from this point until the bottom fiber, there is an area. This is this area, and the centroid of this area respect to the neutral axis is the y bar, and that's Q. Okay, you could also wonder, what if P is above the neutral axis? Is this case? We have the same expression, but Q, that is y bar times A, turns this. The area is the area between P and the top of the area, and the y bar is the centroid of this area from the neutral axis. Also, you can consider the case where you are looking for the shear stress right here at a point in the neutral axis. In that case, you have 2q, y bar times A above and another below. Maybe you have to consider calculate both to compare which is bigger. Another interesting consideration is if you try to find the shear stress at the top of the bottom of the area, you find that is 0, because in the Q expression the area turns 0. For example, if the point P were right here, you have no area below. If the point P be here, there is not area above, so is 0 the shear stress on that point. But when calculated at the neutral axis, the yellow one, is maximum, since the area, as I mentioned before, generate a maximum Q that could be estimated above or below.